Very good. Well, thank you, everybody, for your perseverance. I know in some ways we're asking everyone here to drink from a fire hose, but I think it just reflects that there's quite a bit of remarkable technology development underway. What we know about methanol is a lot more than your grandfather knew about methanol, or what the oil industry told your grandfather about methanol. So I think with that, we're quite in a good position to appreciate our next presentation. It's my pleasure to introduce Professor Sebastian Verhelst. He's in the Department of Flow, Heat, and Combustion Mechanics. He's a member of the Faculty of Engineering and Architecture at Gent University. He's received his advanced degrees in electrical engineering and his PhD in electromechanical engineering at Gent. So that obviously provides a tremendous platform for making a real contribution to our field, and we look forward to hearing his views on high-efficiency methanol applications. So with that, please welcome Dr. Verhelst. Thank you.
So good afternoon once again. Now before I get started with high-efficiency methanol engines, latest research and promising next steps, allow me to just take a step back initially and explain you a bit about the background of us focusing on methanol engines. So the internal combustion engine research focus at Gent University is relatively wide, but includes alternative fuels primarily. And since a couple of years, we're focusing on methanol for a number of reasons. A couple of years ago, we did the exercise of trying to plot out a vision on long-term energy supply and the energy carrier that would be suitable for transportation, because we think these will go hand in hand. And we did that based on a very limited set of base criteria that we set out for potential energy carriers and powertrains. So some really simple base criteria to start with. First of all, obviously, sustainability has to be one of them, which includes, for instance, using a closed cycle for making the energy carrier, but also recyclability, for instance, of the materials that you use to build your powertrain. That in itself obviously is not enough. We think a very important one that's often missing in a lot of studies is scalability. So if you think about the current challenge for transportation, worldwide we're talking about over 1 billion vehicles these days, so a tremendous challenge. So you always have to weigh your probable or possible alternative against scalability. Look at the resources that you need, for instance, to produce your energy carrier. Look at the resources that you need to produce the powertrain. Can you scale that up to those huge numbers? If you have to rely on a scarce resource, there's a no-go there. So scalability is also a very important issue. And then third, of course, there are a lot of other criteria, but this is the base set we started out with. We're talking about transportation, so we need the energy carrier to have high energy density. We need the powertrain to have high power density in order to power transportation. So taking these three criteria, what did we end up with in terms of truly sustainable transportation? We think the answer lies in obviously renewable things, but renewable fuels, and preferably liquid fuels. So renewable could be from solar. That's our main sustainable energy source in the long run. Of course, it depends on where you are around the world, what you're going to rely on exactly. But so say solar fuels, liquid electricity, as we've already heard mentioning. So liquid because that's a very efficient way and thus a practical and cheap way of distributing your energy carrier and storing it either on board, at fueling stations or on board vehicles. For the powertrain, we ended up with a tried and tested internal combustion engines. We know there's a lot of other alternatives out there, but we still strongly believe in the internal combustion engine for a number of reasons. First of all, it's cheap to produce. And why? Because it's produced from abundantly available materials, most of which are being recycled right now already. Next, we've also already heard mentioning about that. A big advantage is it's fuel flexible. Remember the story about Gent fuels and things like that. Plus it has a high power density, and actually it might be the technology with the highest ratio of efficiency to cost. A lot of people still view the internal combustion engine as being a very low efficiency technology. I hope you're aware that we've had tremendous progress in recent years, so that this is not true anymore. And there's still a lot of potential for efficiency improvement. And definitely if you weigh the efficiency you can get out of an engine versus the costs, it's becoming really interesting. So I hope this explains our motto within the research group, being keep the engine but change the fuel. So what about that fuel? Well, we've heard a number of times today the case for methanol being presented. So I'll just quickly go through this, not going into any detail here. We've heard that methanol is a very versatile energy carrier, can be produced in different ways. So although it's primarily being produced from fossil fuels as of today, there are also routes based on biomass, based on wastes, and ultimately, in the long run, of course, a really attractive option is to synthesize it using renewable energy, where you see possible schemes depicted over there. And again, reiterating that it's liquid. So you can rely on cheap tanks that you can place anywhere you like, for instance, in a vessel. You have a cheap way of distributing this energy carrier. Also very interesting is the fact that it's not only miscible with gasoline, it's also miscible with ethanol, which used to be the most prevalent alternative fuel for passenger cars until it was passed by methanol actually recently. And those two things combined mean that you can really work on an evolution of the infrastructure. We were relying on a liquid fuel infrastructure. Right now we're using a number of fuels already. So we have inroads to start introducing methanol. And options like with these Gent fuels means that you have drop-in fuels, that you have vehicles out there that are already able to take on this methanol containing fuel. It doesn't stop at being a fuel. It also serves as a building block for more complex hydrocarbons through the methanol to olefins process. So it's really a compound that can serve a lot of needs, which I hope explains why this has been a focus fuel for us since 2009. And it's really heartwarming to see this big show up, and thank you again for being invited. It's really nice coming from 2009 and having the feeling a bit of being a lone warrior in at that time the methanol engine world, and having to explain myself everywhere I went why we on Earth would be looking at methanol, up to this moment where every 3 or 4 months there's a new gathering concerning around methanol engines. So that's a really good thing. So coming now to the actual topic of this presentation, methanol as an engine fuel. We've already heard a number of methanol properties being really interesting as engine properties. Much of it is determined by methanol's polarity. Much of the differences compared to gasoline are determined by the polarity. So just a few examples here. The higher heat of vaporization, for instance, we're talking about 3 times as much for methanol compared to gasoline on a mass basis, and this is amplified in the engine because of the reduced air-to-fuel ratio. It is a challenge for cold start. We've already heard mentioning about that, but on the other hand, it's great for engine efficiency, emissions, as well as performance. So sort of the holy trinity for engine R&D. This trade-off you usually have between efficiency, emissions, and performance. You can skip a lot of these trade-offs while using methanol. On the downside, it's corrosive to some metals, but this is very well understood and can perfectly be addressed. So not actually an issue. Additionally, it has a high octane number, as we've also already heard mentioning. So you see methanol compared to RON 95 gasoline fuel, which obviously translates to increased efficiency if you have the engine strategy for that. Has a higher burning velocity, which in itself is already good for efficiency. You're better approaching the thermodynamic ideal. But also that usually means that you have more tolerance to dilution. So you can go to lean operation, you can start blending in exhaust gas with the fresh mass, which both mean, again, that you're doing good things for the efficiency and you're lowering temperatures, so you're doing good things for NOx emissions. So we did a number of measurements. First of all, we wanted to find out the potential in what you could call the world standard gasoline engine, which is still, as of today, the port fuel injected gasoline engine. So what happens if you convert such an engine to allow alcohol operation or methanol operation? We converted 2 engines and started measuring just with a simple conversion what we got in terms of efficiency. While using the same operating strategy as the baseline gasoline engine, we already obtained relative efficiency benefits of methanol versus gasoline of the order of 10%. And more importantly, perhaps, reductions of engine out NOx levels of the order of 5 to 10 grams per kilowatt hour engine out. If you take advantage of the dilution tolerance or the increased dilution tolerance of methanol compared to gasoline and start pushing a bit more, but just playing around with the software, so same hardware, but playing around with strategies, that allows you to get relative additional benefits of the efficiency of the order of 5%, and again, you end up with lower NOx emissions. So that's for the port fuel injected base gasoline engine. What would be the potential in a dedicated engine, an engine that makes better use of these particular properties of methanol? We have some idea. There's still a lot of work to do there, but what we did was, while taking inspiration from Merck at EPA by Matt Bruster, to convert a VW turbo diesel to methanol port fuel injected spark ignition operation. So took out the diesel injectors, replaced them with spark plugs, mounted methanol injectors in the intake manifolds, and that was pretty much it. So we didn't touch the compression ratio, remained at the original 19.5 to 1, didn't touch the turbocharger. And so we first of all wanted to reproduce the EPA work because we were quite impressed with the numbers they were getting, but we also wanted to expand that to lower loads, because we then wanted to use the measurement results to feed into vehicle driving cycle simulations. So why would this engine make better use of methanol's properties? Well, we expected a faster and more stable combustion for the high dilution strategies, because it's, as I've said, a high compression ratio engine, turbocharged. So overall temperature levels are higher, which should boost the tolerance for dilution. And overall peak temperatures would be lowered as a result of that, and we were hoping for better efficiency and lower emissions. So what did we get? Well, first of all, efficiency numbers. Here you see an engine map where engine load is represented by brake mean effective pressure on the y-axis and engine speed shown on the x-axis. And so plotted are brake thermal efficiency numbers. And just to focus your attention, the peak efficiency we obtained was 42%, just a basic low-tech conversion, you could say. And this peak efficiency was actually higher than the baseline diesel engine. Also, because of the dilution strategies, being able to control the engine power outputs by playing around with the amount of exhaust gas recirculation, we could get part load efficiency gains of up to 20%. So compared to what is normally an SI type of engine operation using the throttle valve. We were perhaps even more surprised when we looked at the measured NOx numbers, which you see here again in an engine map. NOx emissions engine out shown in parts per million. So really vast engine out NOx reductions of the order of ppm engine out. That's pretty impressive, and that's a result of the very high amounts of EGR, of exhaust gas recirculation we could use. We went up to 50% EGR. So the bottom line here is that you can obtain diesel-like efficiencies while using cheap after-treatment systems, because this engine is still operating lambda 1, but using EGR. So 42% in itself perhaps isn't as impressive as the numbers you've already seen from Martin, but remember, this is a really straightforward, low-cost conversion, not much optimization going on, and already you're attaining the same or even higher efficiencies as the baseline diesel. So that's an important message, I think. So what's the potential in state-of-the-art gasoline engines? We've talked about PFI engines. What about if you go and look at direct injected engines? Well, we cooperated with the Argonne National Lab in Chicago. We tested their DI, naturally aspirated engine in the lab, on methanol, on gasoline, on ethanol, butanol, E85 and M56. You might remember that this M56 blend is a binary blend that ends up having the same air-to-fuel ratio as an E85, which means that this is a fuel you could potentially introduce in a flex fuel vehicle without the engine control unit realizing that it's not operating on E85 but actually on M56. We did use the stock ECU, which meant we had some load limitations because of the lower heating value of methanol. You have to have longer injection durations for a certain power output. So there were some limitations there, but still at low to mid loads we recorded a 2.7 percentage point efficiency increase on methanol versus gasoline, and this increased at high load where you can really make use of the higher knocking resistance of methanol, and in the end we obtained a peak efficiency there of 40%, which given the baseline engine again was quite impressive, and combined with the carbon to hydrogen ratio of methanol translates to a 20% reduction in CO2 numbers compared to the baseline gasoline engine. And we're currently following this up with looking at a downsized engine. We are doing tests as we speak on a 1.6 liter turbocharged gasoline engine with direct injection, so-called T3 Volvo engine. We have already shown for low loads 5 percentage points higher efficiency, translating to 18% relative increase and about a third lower engine out NOx emissions. We've also just started picking up on the idea that was already briefly presented by Leslie Bromberg from MIT, this fuel reforming using exhaust heat. So methanol is a compound that's very suitable for exhaust energy recovery. So reminding you of the idea, if you look at your methanol tank there, what you could do is make use of your exhaust heat to reform your methanol and end up with a hydrogen-rich gas that has a higher heating value than the methanol you started with, because it's an endothermic reaction. So you make use of the heat that would otherwise be wasted. And not only that, because it's a hydrogen-rich gas, you can further push these dilution strategies. You can go to leaner mixtures or to higher EGR rates, for instance. So there's a potential for pretty high efficiencies. I'm just reminding you of the figures that Leslie was talking about. So really appealing figures, I would say, which is a justification for a PhD that was just started at Gent, where we are going to try to actually build this thing and see whether we can come up indeed with these efficiency numbers. So I've been talking about SI engines now. What about diesel engines? We've also recently started work. And Josef already mentioned the Lean Ships project this morning. It's a Horizon 2020 project sponsored within the Mobility for Growth pillar, which is aimed at lowering the energy use and the emissions emitted by the shipping sector. It's a relatively big project involving 46 partners and 8 demonstrator platforms. And one of these 8 demonstrator platforms is called Demonstrating the Potential of Methanol as an Alternative Fuel, which includes 6 partners. So ourselves are leading the work package. We have 2 shipyards involved. We have an engine supplier involved, ship owner, and Methanex is also involved as a methanol producer and supplier. The main work will be to convert a high-speed marine diesel engine to dual fuel operation with methanol. So making use of a pilot injection of diesel to serve as an ignition source and trying to increase the energy share of methanol as much as possible, methanol being introduced in the port. We've also just heard that this might not be the best approach in terms of efficiency or efficiency versus emissions trade-off. We're fully aware of that. The reason we chose this type of technology is first of all because we want to be able to offer a retrofit solution. We've heard about the importance of that in the shipping industry, and we also want to lower the thresholds of acceptance of possible ship owners, because using this option, you could revert back to 100% diesel operation if you would have any issues with the methanol system. So it's more from the viewpoint of acceptance and introduction in the market that we've picked this technology. We're going to include a life cycle assessment of methanol in shipping for 2 case studies that we've selected to make it a bit more concrete, to come up with actual numbers, to try to convince people at the end of the project, because this is also a part of that, to hopefully take this up and hopefully translate this to a number of actual pilots. Then finally, I've been mostly talking about our experimental work. I just want to share a few words with you on our simulation work. All of these tests that I've just been mentioning obviously rely on extensive bench measurements. The alternative, or at least the part of the replacement of that, could be through engine simulation. So we've been working on supplying a number of building blocks, some fundamental combustion data on methanol and methanol blends, and we've been using these building blocks in so-called multizone thermodynamic modeling. So it's getting a bit technical now, but bear with me. So what I mean with building blocks are, on the one hand, for instance, the laminar burning velocity, the fundamental burning velocity of methanol containing mixtures. Sort of groups the chemical effects on combustion, so it's a convenient way of including the combustion properties in any engine simulation. We calculated this laminar burning velocity using a selected chemical kinetics scheme, and then built a correlation that allowed easy use in an engine code, and then went on to validate this through measurements. On the top right, you see a picture of the flat flame burner at Lund University, where we measured a number of mixtures. There was a burning velocity to validate the correlation, and beneath that you see a spherically expanding flame, which is measurements we did in cooperation with Leeds University. And we did this for pure methanol as well as methanol mixtures. So these gem blends, we know also how to model them. Another important property is the auto-ignition delay time, which is it determines the resistance to engine knock, so it's important to get right. Pretty similar story as with the laminar burning velocity. And did a lot of calculations to build a correlation for use in engine code, and did that for pure methanol as well as these gem blends or other alcohol mixtures in general. And then we looked at multizone thermodynamic engine models, which are sort of a compromise between you want accuracy, but you don't want too much computational effort if you want to use a code to really optimize engines for a different fuel, so for methanol in this case. So we use this as a framework for testing our correlations, where we used our in-house code to calculate through the power cycle, and then used the commercial code to include the gas dynamics. We evaluated these correlations as well as models for turbulent combustion velocity, and actually the whole experimental campaign I started out with was done to serve as a database for our modeling efforts, but luckily they turned out to be interesting in their own right. But that means that we ended up with a quite extensive database with variations of different engine parameters, and allowed us to validate these correlations. So we looked at normal as well as knocking combustion, where for improved predictions for knocking combustion, we're still working on improving the puddling model as well as in-cylinder heat transfer. So to conclude, I think the case for methanol as an energy carrier has been made, but additionally, methanol is a great engine fuel. It allows increased performance, increased efficiency, and decreased emissions. So actually you end up with the potential for efficiencies exceeding those of diesel engines, with the low emissions of gasoline engines, and with greater performance than both. So pretty compelling story. We have already partly confirmed this potential in engine testing, where we're planning more tests on the GDI engine and on the reformer setup. And we're also working on supporting this by engine simulation to accelerate this experimental campaign. So I've talked about the contributions to the building blocks and the initial demonstrations of predictive engine cycle simulations. So that's it. Thank you very much for your attention.